What if the very fabric of space and time could be folded and twisted, creating a shortcut that lets you step into the past or leap into the future? Time travel has fascinated humanity for generations, inspiring countless stories of adventurers rewriting history or exploring distant futures. But what if this concept wasn't just the stuff of science fiction? Enter wormholes, an intriguing theoretical idea born from Einstein's general theory of relativity. These potential cosmic shortcuts have captivated not only our imagination, but also the minds of physicists and futurists who see them as a possible gateway to making time travel a reality. Today, we're diving into the science, the technology, and the challenges standing in the way of transforming this mind-bending vision into something tangible. From the physics behind wormholes to the breakthroughs that could one day make them accessible, get ready to explore how the impossible might just become possible. Let's unravel the secrets that could turn the pages of time into a pathway we could one day walk. So, what exactly are wormholes? Picture them as cosmic shortcuts through the vast fabric of spacetime, like tunnels with two openings, one at each end connecting distant points in the universe. Instead of traveling billions of years across endless voids, a wormhole would, in theory, allow you to step through one end and emerge almost instantly at the other, no matter how far apart they are. This mind-boggling concept first emerged in 1935 when Albert Einstein and physicist Einstein-Rosen published a groundbreaking paper introducing what they called Einstein-Rosen bridges. These bridges, or wormholes, were theorized as solutions to the equations in Einstein's general theory of relativity, essentially warping spacetime into a shape where two distant regions could be directly linked. To understand how a wormhole might work, imagine spacetime as a vast, flat sheet of paper. If you draw two dots on the paper, one representing Earth and the other a galaxy millions of light years away, and try to connect them, you'd usually draw a straight line. This line represents the long, traditional journey through normal space. But now, fold that paper so the two dots line up with each other and punch a hole through both layers. Suddenly, the two distant points are directly connected by a tunnel, a much shorter path than the original line. This is the essence of a wormhole, a theoretical structure where the throat of the tunnel links the two openings, or mouths, seamlessly bypassing the unimaginably long distances of normal space. The idea becomes even more fascinating when you consider that wormholes might not just connect different places in space, they could also connect different times. In other words, stepping through a wormhole might allow you not only to travel across galaxies, but also to travel into the past or the future. While we're far from proving this in practice, the concept opens up thrilling possibilities for time travel. Could wormholes be the key to unlocking the secrets of the fourth dimension? To answer that, we need to dive deeper into their physics, stability, and whether humanity could ever construct or control these passageways through time and space. Wormholes owe their theoretical existence to Einstein's general theory of relativity, which fundamentally changed the way we understand the universe. At its core, the theory describes space and time, not as two separate entities, but as a single, interconnected fabric called spacetime. And here's the fascinating part: spacetime isn't fixed. It can bend, stretch, and even twist under the influence of massive objects like stars, black holes, or, in this case, extreme energy configurations. This malleable nature of spacetime is where wormholes find their roots. Einstein's equations show that if you could warp spacetime severely enough, you might create a shortcut, a wormhole. Imagine spacetime as a stretchy rubber sheet. If you place a heavy object like a bowling ball on the sheet, it creates a dip, a curve. Now, what if you could punch through that sheet, creating a tunnel from one side to the other? That's essentially what a wormhole would do. It would connect two distant regions of spacetime by bending and warping the sheet so intensely that the 2 points touch. The wormhole would act as the tunnel between them, bypassing the normal distances of space. But wormholes don't just promise shortcuts through space. They could also bend time itself. This is where another aspect of Einstein's theory comes into play: time dilation. In environments with extreme gravity or high speeds, like near a black hole or a fast-moving spaceship, time moves at a different rate compared to areas with weaker gravity or slower speeds. It's not science fiction, it's been experimentally confirmed. Astronauts aboard the International Space Station, for instance, experience time ever so slightly slower than people on Earth because of the station's incredible speed and the weaker gravity in orbit. Now apply this concept to a wormhole. If the two ends of the wormhole were in regions of spacetime experiencing different rates of time dilation, say, one near a black hole and the other farther away, time would flow differently at each mouth. In theory, this means you could enter the wormhole at one end in, say, the year 2300 and emerge at the other end in the year 2200. In this way, wormholes could act not only as bridges through space but also as portals to the past or future. While this paints an exciting picture, it's important to note that these ideas remain mathematically possible but unproven in practice. The extreme conditions required to create and maintain such a structure push the limits of our current understanding of physics. Still, the connection between wormholes, spacetime curvature, and time dilation offers a glimpse into how time travel might one day become scientifically plausible, at least on paper. But before we can dream of stepping through a wormhole, there's a massive hurdle to overcome: stability. Could a wormhole even exist long enough for anything or anyone to travel through it? That's where the real challenges begin. Now, let's address one of the biggest hurdles in turning wormholes into functional time travel portals: stability. Theoretical physics does allow for the existence of wormholes, but there's a catch: they're inherently unstable. Without some extraordinary intervention, a wormhole would collapse almost instantly after forming, like a tunnel through soft sand that caves in before you can even step inside. This means that, in their natural state, wormholes wouldn't remain open long enough for anything, light, matter, or even information to travel through. To understand why this happens, consider the immense forces at play. The walls of a wormhole are under constant tension from the surrounding spacetime, which tends to pull them closed. Add to that the gravitational effects of anything trying to pass through, and the situation becomes even worse. Imagine trying to hold open a gigantic, flexible tunnel while also bracing it against the weight of an entire universe. It gives you an idea of the immense challenge wormholes present. This is where exotic matter comes into the picture. Exotic matter isn't like the ordinary matter around us: protons, neutrons, and electrons that make up everything we see and touch. Instead, exotic matter is a hypothetical form of matter with negative energy density and negative pressure. In simpler terms, it behaves in the opposite way that normal matter does, effectively counteracting gravity. This unusual property means exotic matter could, in theory, act as a kind of scaffolding to keep a wormhole open. By lining the throat of the wormhole with exotic matter, you could push spacetime outward enough to prevent the tunnel from collapsing under its own weight. But here's the problem: exotic matter isn't something we've ever observed or created. It exists only in mathematical equations and theoretical models. Even if it does exist somewhere in the universe, we'd need an enormous quantity of it, all in the right place at the right time, to stabilize a wormhole. And that's just the beginning of the engineering challenges. The energy required would be astronomical, far beyond anything we can currently harness. To put it into perspective, keeping a wormhole open might demand energy comparable to converting the mass of an entire planet directly into energy. something far outside humanity's current capabilities. Then there's the issue of catastrophic collapse. Even the slightest miscalculation in the structure or stability of a wormhole could cause it to snap shut instantly, potentially destroying anything or anyone inside. The risks wouldn't just be personal, they could pose a threat on a cosmic scale. A destabilized wormhole could, in theory, release massive bursts of energy, disrupting nearby regions of spacetime in unpredictable and potentially catastrophic ways. What's even more intriguing is the question of whether stabilizing a wormhole might violate the known laws of physics. Negative energy density, for example, pushes the boundaries of what we understand about the universe. While some experiments, like those involving Casimir effects, hint at phenomena resembling negative energy on a tiny scale, scaling this up to cosmic proportions remains a massive leap, one that might not even be possible within our current framework of physics. In short, even if we could pinpoint the location of a naturally occurring wormhole, traversing it would require solving some of the toughest engineering and theoretical challenges humanity has ever faced. Keeping such a structure stable isn't just difficult, it's a barrier that requires us to rethink the very laws that govern our universe. Could we one day discover a workaround, or are the challenges so insurmountable that wormholes will remain forever confined to the realm of theory and imagination? It's a question that highlights just how much we still have to learn about the complexities of spacetime. The possibility of wormholes doesn't just push the boundaries of human imagination, it also challenges the very foundations of modern physics. This has sparked decades of debate among scientists about whether these cosmic shortcuts are purely theoretical constructs, or if they could actually exist within the framework of the universe's laws. While Einstein's equations hint at the possibility of wormholes, the leap from elegant math to tangible reality is far from certain. Some physicists, like Kip Thorne, have been at the forefront of exploring these ideas, offering tantalizing insights while also acknowledging the significant roadblocks in proving their feasibility. Kip Thorne, one of the world's leading experts in gravitational physics, brought the concept of traversable wormholes into the spotlight in the late 20th century. He even collaborated with Carl Sagan on incorporating wormholes into the novel Contact, making the idea more accessible to the public. Thorne and his colleagues demonstrated mathematically that, with the right conditions, a wormhole could theoretically allow matter to pass through safely. However, these same calculations underline how precarious such structures would be. The reliance on exotic matter, as we discussed earlier, and the extreme energy requirements make many physicists skeptical about whether wormholes can ever exist beyond the pages of theoretical research. But the controversies surrounding wormholes don't stop there. Let's talk about time travel, one of the most thrilling and problematic implications of traversable wormholes. If wormholes allow you to connect 2 points in spacetime, they could also provide a way to travel to the past or the future, raising profound questions about causality and the very nature of reality. One famous thought experiment is the grandfather paradox. Imagine you travel through a wormhole to the past and accidentally or intentionally prevent your grandfather from meeting your grandmother. This act would erase your own existence, causing a paradox. If you were never born, how could you have traveled back in time in the first place? It's a mind-bending loop that seems to defy logic, and it's exactly this kind of paradox that fuels skepticism about the feasibility of time travel through wormholes. To make sense of such paradoxes, physicists turn to the concept of closed timelike curves, or CTC. A closed timelike curve is essentially a loop in spacetime that allows you to return to your starting point potentially even before you left. Wormholes, if properly configured, might create such curves, enabling time travel. But CTCs introduce a deeper problem. They appear to violate causality, the principle that cause precedes effect. If events can influence the past, does that mean the past, present, and future are all tangled together in some kind of cosmic feedback loop? While some physicists propose that the universe might self-correct to prevent paradoxes, an idea called the Novikov self-consistency principle, others argue that CTCs fundamentally contradict how we understand the universe to work. These debates reveal how wormholes occupy a strange space between possibility and impossibility. On one hand, they're mathematically plausible solutions to Einstein's equations. On the other hand, they challenge some of the most cherished principles of physics, from causality to energy conservation. This tension fuels the ongoing mystery. Are we simply missing a crucial piece of the puzzle? Or do wormholes point to limitations in our current understanding of spacetime itself? As we continue to explore the universe and push the boundaries of technology, the answers may come, just not in the ways we might expect. From advanced particle accelerators that could reveal hidden properties of spacetime to quantum computing that might provide new insights into exotic matter, future innovations could hold the key to resolving these controversies. Could we one day overcome the paradoxes, stabilize a wormhole, and unlock the secrets of time travel? It's a question that keeps physicists and dreamers tantalizingly curious. Let's take a closer look at the futuristic technologies that might turn these scientific debates into revolutionary breakthroughs. Advancing toward the reality of wormholes, even in the most speculative sense, will require a technological revolution. The challenges we've outlined, stability, immense energy requirements, and precise manipulation of spacetime, are monumental, but emerging technologies are laying the groundwork for humanity to push the boundaries of what's possible. Let's explore a few cutting-edge innovations that could one day bring the exploration or even creation of wormholes within reach. One of the most promising tools in this theoretical quest is quantum computing. Unlike traditional computers, which process information in binary, ones and zeros, quantum computers leverage qubits, which can exist in multiple states simultaneously thanks to the principles of quantum mechanics. This incredible processing power allows quantum computers to tackle problems that are far too complex for classical machines. Simulating spacetime geometries, such as the formation and behavior of wormholes, is one such challenge. These geometries are governed by enormously complicated equations that describe how mass, energy, and gravity interact on the most fundamental level. Quantum computing could allow scientists to map out these interactions in unprecedented detail, giving us a clearer understanding of how wormholes might form, behave, and crucially, remain stable long enough for practical use. Then there's high-energy particle physics. Facilities like the Large Hadron Collider, the world's most powerful particle accelerator, are designed to mimic the extreme conditions of the early universe. By smashing particles together at nearly the speed of light, these experiments generate conditions of immense energy and heat, creating tiny, fleeting glimpses of phenomena that could include microscopic wormholes. While no evidence of such structures has yet been observed, some theorists believe that under the right conditions, high-energy collisions could briefly open tiny wormholes too small and short-lived for practical use, but enough to provide indirect proof that wormholes are possible. These experiments help refine our understanding of the universe's fundamental building blocks and could eventually point us toward the conditions necessary to create larger, more stable wormholes. Now, when it comes to the energy requirements for creating, or at least stabilizing a wormhole, the scale is hard to fathom. We're talking about energy levels far greater than anything we can currently produce, even with the most advanced fusion reactors. But speculative technologies like Dyson spheres offer a glimpse into how future civilizations might harness the required power. A Dyson sphere is a theoretical megastructure that could envelop a star, capturing a significant portion of its energy output. Such a device could provide the astronomical energy needed to manipulate spacetime, while Dyson spheres remain firmly in the realm of science fiction for now. They represent the kind of bold thinking required to address the energy problem. Another intriguing possibility is antimatter. Antimatter is the mirror image of ordinary matter with opposite charges. When matter and antimatter collide, they annihilate each other, releasing pure energy. In theory, an antimatter engine could generate the levels of energy needed to stabilize a wormhole. While antimatter is currently produced only in minuscule amounts in particle accelerators, advancements in this field could one day make it a viable source of power for extreme applications like spacetime manipulation. These technologies may sound far off, but they align with futuristic concepts already being imagined by scientists, engineers, and visionaries. They represent the next steps in humanity's efforts to unravel the mysteries of the cosmos, whether through direct experimentation or by fueling our imaginations with what might be possible. If history has taught us anything, it's that today's wild theories often become tomorrow's groundbreaking discoveries. Could the technologies we've discussed serve as the stepping stones toward unlocking the secrets of wormholes? Or will they lead us to an entirely new understanding of the universe that we've yet to even conceive? Regardless of the outcome, these advancements bring us closer to answering one of the most profound questions of all. Can we ever bridge the vast distances and times that separate us across the cosmos? Let's take a moment to reflect on where this journey could take us next. When it comes to wormholes, much of what we've explored so far remains purely theoretical. But what happens when we start speculating about the future, about technologies and civilizations that might one day turn these theoretical constructs into practical tools? This is where speculative physics takes center stage, with concepts like traversable wormholes, artificial wormholes, and futuristic energy systems that could redefine not only space exploration, but also how we perceive time itself. Let's start with the idea of traversable wormholes, a concept championed by physicists like Matt Visser. Building on earlier work by Kip Thorne and others, Visser explored more refined models of wormholes that don't just remain stable, but are also large enough for objects or even spacecraft to pass through. These traversable wormholes rely heavily on the existence of exotic matter, as we discussed earlier, to counteract the immense gravitational forces trying to collapse the tunnel. While exotic matter remains hypothetical, Visser's work gives us a clearer framework for imagining how future technologies might manipulate spacetime to create passageways that are not only stable but also usable. These models push the boundaries of our understanding, suggesting that such wormholes could connect not just 2 points in space but 2 points in time, effectively merging the concepts of interstellar travel and time travel into one. But what if wormholes don't naturally occur in the universe, or if natural ones are simply too unstable to ever be useful? This is where the idea of artificial wormholes comes into play. Instead of searching for wormholes, some physicists theorize we might one day engineer them ourselves, using powerful gravitational fields or advanced quantum technologies. Future civilizations might manipulate spacetime directly, creating synthetic wormholes tailored for specific purposes. For example, imagine a society capable of generating and stabilizing these structures for instantaneous travel from one point in the galaxy to another, bypassing the need for slower methods like warp drives or cryogenic space travel. A technological leap like this could fundamentally change the way we interact with the cosmos, opening up not just our galaxy but potentially the entire universe to exploration. To understand how such feats might be achieved, we need to consider the role of future civilizations. This brings us to the Kardashev Scale, a way of classifying advanced civilizations based on their ability to harness and control energy. Humanity, for now, is still at a Type 1 level, harnessing energy on a planetary scale. But a Type 2 civilization would be capable of capturing the energy of an entire star, while a Type 3 civilization could command the energy of an entire galaxy. A Type 2 civilization might construct something like a Dyson sphere, a massive structure designed to harvest a star's power, to generate the vast amounts of energy needed to create or sustain a wormhole. A Type 3 civilization, on the other hand, might manipulate black holes or other cosmic phenomena to engineer wormholes on an even grander scale, enabling not only interstellar but intergalactic travel. These speculative models don't just hint at the future of exploration, they also open the door to time travel. If artificial wormholes could manipulate spacetime in precise ways, they might enable controlled travel to the past or future. Imagine a civilization capable of sending observers back to witness pivotal moments in history or projecting explorers forward to study the unknown landscapes of a distant age. This kind of capability could revolutionize fields like archaeology, anthropology, and even science itself, allowing us to directly interact with moments long gone or yet to come. Of course, the implications of such technology go far beyond science. The societal and ethical questions are just as profound. Would time travel through wormholes be regulated and controlled, or would it lead to chaos as individuals or groups attempt to manipulate history? What would it mean for our sense of identity as a species if we could travel to distant stars instantly or visit other epochs in time? These are questions no civilization has ever had to grapple with before, but they would become unavoidable in a world where artificial wormholes are a reality. While all of this remains firmly in the realm of speculation, these theories and models inspire us to dream big and imagine a future where wormholes are as essential to travel as airplanes or rocket ships are today. And as we push the boundaries of physics and engineering, we may inch closer to turning these grand ideas into a breathtaking reality. Let's take a moment to step back and reflect on how such breakthroughs could reshape not only our understanding of the universe, but also the very fabric of human society itself. The prospect of time travel through wormholes isn't just a scientific and technological challenge, it's a profound ethical and societal one. Imagine for a moment a world where stepping into the past or leaping into the future is as accessible as booking a plane ticket. While the scientific breakthroughs that could enable this are exhilarating, the implications for humanity are staggering. How would we handle the ability to alter history or foresee what's yet to come? Would we use this power wisely, or would it plunge society into chaos? One of the most immediate concerns is the sheer responsibility of reshaping the past. If wormholes allowed us to travel to moments in history, the temptation to alter the timeline could be overwhelming. On one hand, such a capability might seem like an opportunity to right past wrongs, prevent large-scale tragedies, or shape a better future. For instance, would we go back and stop catastrophic wars or intervene before natural disasters claimed lives? The idea is compelling, but it quickly becomes clear how delicate and dangerous this would be. Even the smallest change could ripple outward, fundamentally altering the course of history in ways we can't predict. What if preventing one tragedy inadvertently causes another? These are the kinds of moral dilemmas that time travel would thrust upon us. Who gets to decide what can and cannot be altered, and how would societies enforce these decisions? Without a clear ethical framework, the ability to alter time could lead to unintended consequences, or even outright manipulation of history for personal or political gain. This brings us to another ethical concern: the potential for exploitation. Wormhole-based time travel could easily become a tool for those seeking power. Imagine governments or corporations using it to secure resources from the past, gain insider knowledge of future events, or rewrite history to serve their narratives. The potential for corruption and abuse is enormous. Could laws or international agreements even begin to regulate something this revolutionary? And more importantly, would humanity be able to resist bending the rules when the stakes are so high? These possibilities highlight just how much responsibility comes with this kind of power and how easily it could spiral out of control. But the ethical implications don't stop at the collective level. Time travel would also have profound psychological effects on individuals. For example, how would it feel to visit a future where your loved ones are long gone? Or to return to a past version of yourself and confront your younger self's choices? These experiences could fundamentally alter your sense of identity, leaving you questioning who you are and where you belong in time. Even more unsettling is the possibility of encountering alternate versions of the timeline or even alternate versions of yourself. What would it mean to meet a you who made different decisions, lived a different life, and became someone entirely unrecognizable? The existential questions this raises are enough to make anyone pause. Would time travelers be prepared to grapple with the psychological weight of these encounters, or would they struggle with feelings of disorientation, regret, or even guilt? On a broader scale, time travel could reshape how communities and cultures perceive time itself. If the future is knowable, does that mean it's fixed, or can it be changed? How would societies cope with the knowledge of what lies ahead? Would hope and ambition fade if people became too focused on avoiding mistakes or chasing guarantees? And what would happen to our understanding of free will if our future selves could influence our current decisions? These questions also dive into the philosophical realm. If time travel allows for multiple timelines or alternate realities, how do we define the timeline? Which version of history takes precedence? And what happens to the moral weight of our actions when every possibility might occur in some parallel world? This could redefine everything we know about fate, choice, and the nature of existence itself. Ultimately, these ethical and societal questions remind us that time travel through wormholes, while scientifically thrilling, is about far more than equations and technologies. It's about humanity's ability to wield this power responsibly without losing sight of what makes us human. And as we continue to explore the mysteries of time and space, we'll need to consider whether we're ready, not just scientifically, but morally and culturally, for the profound changes this technology could bring. So, where does this leave us? How do these implications shape our evolving understanding of time and our place within it? Let's explore that next. As we peer into the future of wormhole research and time travel, the path is as exciting as it is uncertain. Although wormholes remain theoretical for now, the growing synergy between fields like quantum mechanics, general relativity, and experimental physics holds the promise of breakthroughs that could one day turn the impossible into reality. Scientists are already pushing the boundaries of our understanding of spacetime, inching closer to answers that might unlock wormhole secrets and perhaps their potential as gateways through space and time. Current research projects and experiments provide a glimpse of the strides being made. Take the work happening at facilities like Fermilab and CERN, where particles are being smashed together at nearly the speed of light. These experiments aim to replicate the extreme energy conditions of the early universe, conditions that might reveal phenomena like tiny, transient wormholes. Even though these miniature wormholes, if they exist, would be far too small for practical use, detecting them would be a monumental step in proving that wormholes are possible within the framework of physics. Similarly, advancements in quantum field theory are shedding light on how negative energy, an essential ingredient for stabilizing wormholes, could theoretically be produced or manipulated, even if only on a microscopic scale for now. Beyond experimental physics, there's a growing focus on uniting the two pillars of modern physics, General Relativity, which explains gravity on a cosmic scale, and quantum mechanics, which governs the behavior of particles on the smallest scales. These two frameworks are notoriously difficult to reconcile, but wormhole research lies at the intersection of both, making it a perfect testing ground for new theories. For example, some physicists are exploring the idea that wormholes might naturally emerge from quantum entanglement, a phenomenon where particles remain connected even when separated by vast distances. If entanglement and wormholes are linked, as some theories suggest, it could revolutionize not only our understanding of space-time but also our ability to manipulate it. Now imagine a future where these scientific efforts bear fruit. Picture humanity harnessing wormholes for instant interstellar travel. The ability to reach galaxies that are millions of light years away in a matter of seconds would fundamentally change our relationship with the cosmos. Entire new worlds of exploration, colonization, and discovery would open up, making interstellar travel not just a possibility but an everyday reality. This isn't just science fiction, it's a vision of what might one day be achievable if we can overcome the immense hurdles of stabilizing and controlling wormholes. Or consider the tantalizing possibility of using wormholes to peek into the past. Instead of mere speculation or guesswork, historians and archaeologists could directly observe pivotal moments in human history. Imagine standing in ancient Rome as the Colosseum comes to life, or witnessing the construction of the Great Pyramid of Giza. Such a capability could reshape how we understand and experience history, bringing clarity to mysteries that have confounded scholars for centuries. It's not hard to see how wormhole-based time travel could become one of the greatest tools for expanding human knowledge. But here's the big question: is this future inevitable, or are wormholes destined to remain just out of reach? While progress in physics is accelerating, there's no guarantee that we'll ever overcome the technical, energetic, and philosophical challenges that wormholes present. The universe may well have built-in limits that prevent us from bending space-time to our will. Or perhaps the answers lie in places we haven't thought to look yet, in dimensions beyond our perception, in new forms of energy, or in principles that rewrite what we think we know about reality. We may never fully master the manipulation of space-time, but the pursuit itself could lead us to other, equally transformative discoveries. Ultimately, the future of wormhole research and time travel isn't just about technology or physics. It's a reflection of humanity's boundless curiosity and relentless drive to push past the frontiers of understanding. Whether wormholes become a practical tool or remain a theoretical wonder, they symbolize our deepest desire to explore, to connect, and to comprehend the vast universe we inhabit. And as we look ahead, we must also ask ourselves, if wormholes do become a reality, how will they reshape not just our understanding of the universe but our place within it? These questions remind us that the pursuit of knowledge is as infinite and as mysterious as the cosmos itself. As we wrap up this journey into the mysterious and mind-bending world of wormholes and time travel, let's reflect on what we've uncovered. Wormholes, these theoretical tunnels through space-time, sit at the fascinating crossroads of science fiction and real-world physics. They represent a tantalizing possibility, a bridge not only across galaxies but potentially across time itself. From Einstein's groundbreaking theories to modern explorations in quantum mechanics, wormholes offer us a glimpse into how space-time might be more flexible, more dynamic, and perhaps even more accessible than we ever imagined. But alongside the excitement come immense scientific and ethical challenges. The mathematics shows that wormholes could exist, but their inherent instability, the need for exotic matter, and the mind-boggling energy requirements make their practical use far from reach. Even if we could overcome these hurdles, we would face profound questions about how time travel might impact our understanding of reality, causality, and free will. Can we navigate the delicate balance between science and morality, between pushing boundaries and respecting the consequences of such transformative discoveries? These are questions humanity would need to answer long before taking the first step through a wormhole. Yet, it's clear that our fascination with wormholes is about much more than just physics. They symbolize something deeper, a fundamental part of what makes us human. The desire to explore, to transcend limits, to connect with distant places and times is woven into our very nature. Whether wormholes remain theoretical or one day become a reality, they ignite our imagination and challenge us to think beyond the constraints of what we currently know. They remind us that every leap forward begins with a question. What if? So, while wormholes are still far from being understood, let alone utilized, their very concept inspires us to dream of a future where the barriers of time and space are no longer insurmountable. Even as we explore the unknown with bold theories and cutting-edge technologies, wormholes remind us of the importance of curiosity and imagination in driving scientific discovery. And now, we want to hear from you. What are your thoughts on wormholes and their potential to revolutionize our understanding of time and space? Do you think humanity will ever develop the ability to harness them, or do you believe they'll remain a fascinating theory forever? Share your ideas and questions in the comments below. Your perspective is what makes this exploration even more exciting. Don't forget to subscribe to the channel for more deep dives into the realms of futuristic science, technology, and the mysteries of the universe. Together, let's keep asking the big questions, dreaming of extraordinary possibilities, and exploring the endless frontier of human knowledge. Until next time.